Today our topic is Fraunhofer single slit diffraction. In case of Fraunhofer diffraction, the basic setup is we have to take a monochromatic source of light, and let us consider the monochromatic source of light has a wavelength of lambda, and we have to put a lens, convex lens L1, so that the source should be placed at the focus of our lens, and the output we will obtain the parallel rays. These parallel rays are allowed to fall on a slit. Let us consider the slit is AB, having a width of A. These parallel rays, when strike at the edges of the slit, they get deviated from their path. Let us consider the angle of deviation is theta, and due to this deviation we obtain a diffraction pattern on the screen, and to obtain the diffraction pattern on the screen we have to converge these parallel rays with another convex lens of large aperture area as compared to the first lens. This convex lens converge all these parallel rays at a point, and let us consider the point is P, and from the midpoint of the slit, the midpoint opposite to the C is O on the screen. This is the basic setup of Fraunhofer diffraction. When parallel rays are allowed to fall on a single slit, we find out that due to the phenomena of diffraction on the screen at the opposite of the center of the slit, we obtain a central bright maxima, and the width of the maxima is approximate double as compared to the other maxima which are obtained on both sides of this central maxima. This pattern of maxima, minima, maxima, minima is obtained due to the Fraunhofer diffraction. Why this pattern is obtained, how the width of central maxima is double as compared to the other maxima, why the intensity of the central maxima is maximum whereas the intensity of another minimas, that is another maximas, that is secondary maximas, tertiary maximas, goes on decreasing with the order. Now we will discuss about the central maxima and how these intensities of another maximas goes on decreasing. Again, we are using the basic setup of our Fraunhofer diffraction, and let us consider the slit is AB, having a width of A, and the parallel rays from the convex lens A, first convex lens, is allowed to fall on the slit, and with the help of the second convex lens we are converging these on the screen. And let us consider again, C is the midpoint of the slit, and opposite to C there is a point on screen, and we are denoting it with O. At the edges again we know that the light moves in straight path, but due to diffraction it get deviated by some sort of angle, and let us consider this angle is theta. Every wave is experience same angle of deviation, and after passing through the lens they get converge at a point P. Now as we are seeing in the diagram, the distance traveled by the rays coming out from B to P is large as compared to the waves which are coming from A to P, and this difference between the waves from B to P and from A to P gives us the path difference, and this path difference is responsible to find out or to produce the fringes of darkness or brightness at the screen. Now we will discuss the different cases by which we obtain the darkness or we are obtaining the brightness as above as well as below the center of the screen. Now, to make these distance from B to P and A to P equal, we are drawing a perpendicular from A to BP, and let us consider the point is D where the perpendicular intersect this wave, and as we know that this distance in this sort of triangle is A, and this angle of diffraction is theta, and with this line this is the perpendicular, and with this line this is the perpendicular, and we know that this angle is theta in between these two lines, then we will also obtain this angle is theta because this is the angle in between the lines of the perpendicular. And we have to find out the extra distance which is our path difference. From this triangle, this is our perpendicular, this is our hypotenuse, and this is our base, and we will find out that BD, the extra distance, that is the path difference, comes out to be A sine theta. We will find out A sine theta may be integral multiple of the monochromatic source of light which is used, or maybe it is an odd integral multiple of lambda by 2. These are the two conditions which will define the darkness and brightness condition. Now we will discuss the darkness and brightness condition for the Fraunhoffer diffraction pattern. Now, first case, A sine theta, let us consider it is equal to n lambda, and for simplicity we are considering the first integer n is equal to 1. We will find out that A sine theta comes out to be lambda. It means from A to B, that is with the width of the slit, the path difference from A to B should be equal to lambda. If C is the midpoint, then the wave which is coming from A and the wave which is coming from C, they should face a path difference of lambda by 2. If these waves reaches at point P, then we know that if the path difference is lambda by 2, then the phase difference is pi. If from A the wave is giving a crust at point P, then due to the path difference of lambda by 2, the wave from C gives us a trough at the point P, and they are coming from the same source, so their amplitudes are same, and according to the superposition principle of waves, the amplitude at point P, that should be equal to the sum of these amplitude, that is A plus minus A, and that comes out to be 0. It means we have obtained the condition of darkness here. Similarly, the wave which is coming from C and the wave which is coming from B, again they face a phase difference of a path difference of lambda by 2 and a phase difference of pi. If from C a trough is moving at point P, then we know that due to the extra path difference of lambda by 2, we will obtain a crust from the wave coming from P. Hence, again the wave coming from C and the wave coming from B, they will interfere destructively. And due to this destructive interference, again we get the condition of darkness. Hence, due to the phase difference and path difference of lambda by 2 or phase difference of pi from A to B, all the waves coming from A between A and C or C and B, they will cancel out each other and we will get a dark fringe at the point P at a distance of x from the screen center of the screen O. Similarly, if sin theta is equal to 2 lambda, again we will divide this slit into 4 parts, and due to this we will obtain again a destructive interference because these will interfere destructively. Hence, the condition for the interference is A sin theta is equal to n lambda. This is the condition of darkness. Case second, if A sin theta is equal to odd multiple of lambda by 2, then what will happen? Let us consider the easiest case when n is equal to n. A sin theta comes out to be 3 lambda by 2, which can be written in the form of lambda by 2 plus lambda by 2 plus lambda by 2. Again, if we have a slit with a width of A and which is divided into 3 equal parts, it means this is the distance A by 3, this is A by 3 and this is A by 3, then this point A to A dash will experience a path difference of lambda by 2, A dash to B dash will experience again a path difference of lambda by 2, and from B to B dash the waves coming out from these 2 points have a path difference of lambda by 2. Then what type of pattern is obtained on the screen? We will find out that from the wave which is coming from A and the wave which is coming from A dash, they will destructively interfere. The wave which is coming from A dash and which is coming from B dash, they will destructive interference, but this part is not interfering with any other part. It means some sort of light is coming at the point P, which is not undergoing destructive interference. Hence, we obtain some sort of brightness here. Hence, the condition for the brightness is A sin theta is equal to 2n plus 1 lambda by 2. If n is equal to 2, A sin theta is equal to 5 lambda by 2. Now we have to divide the slit into 5 parts. It means the slit which is firstly divided into 3 parts is now divided into 5 parts. It means as the integer number increases, the light or the wave which is coming from point P will decrease. Hence, due to the integer number, the brightness and the intensity of the brightness goes on decreasing. Now we will discuss the central maxima which is obtained opposite to the midpoint of the slit. Let us consider the second lens which is placed in between the slit and the screen is very near by the slit, and due to which the distance between the screen and the lens becomes approximately equal to the focal length of the second lens, that is L2, and let us consider the focal length is f. And if we will take the distance between O and P is equal to x, then we will find out that from this triangle, if this is theta, this is f, this is x, then tangent theta is equal to x upon f, that is perpendicular upon base. And we also know that a sin theta is equal to lambda when n is equal to 1 in case of the primary minima. The center is O. This is our first minima. This is the point of our first minima. Then in between these two minimas, we will obtain the central maxima. If this distance is x, we know that this distance is also x. Now we have to find out the value of x. From the equation tangent theta is equal to x upon f, and from this condition sin theta comes out to be lambda by a. If theta is very small, we find out that theta is equal to lambda upon a as well as theta is equal to x upon f. From these two equations, we will find out the value of x, that is f lambda upon a, and the width of the central maxima is 2x. So therefore 2x is equal to 2f lambda upon a. Now we have calculated the width or the thickness of our central maxima. As we know that the width is depending upon the focal length. If the second lens have large focal length, then the width goes on increasing. Second factor which affects the width of the central maxima is your monochromatic wavelength. If we use red color light instead of green color light, we will find out for red color the width of the central maxima is large, and for the green colored the width of the central maxima is small. The last factor which affects the width of the central maxima is the width of the slit. If the width of the slit is narrow, then we will obtain large width central maxima. But if the width of the slit is large, then we will obtain a narrow central maxima.